The key to a planet's composition is its size. When planets form, they start off solid, made of rock and ice. If they become big enough, they're able to hold on to huge amounts of gas, hydrogen and helium the most abundant. These become the gas giants, like Jupiter and Neptune. Smaller planets like Earth are primarily rocky and can only hold on to a thin atmosphere. Kepler-22b is in the middle, bigger than all the rocky planets in our system, but smaller than the gas giants. So is it mainly gas or rock? Astronomer Geoff Marcy is attempting to find out. Tonight, he's using the Keck telescope in Hawaii, which he's operating via video link from Berkeley, California, over 2,000 miles away.
So Jeff, I just opened up and did an autofocus. We've got about 0.85 arc second seeing.
That's great. Fantastic.
And we're set up and ready to go on your first target.
Tonight we're going to be observing Kepler-22b, the planet, which is still somewhat mysterious. We don't know whether the planet is rocky like the Earth or gaseous like Jupiter and Saturn.
To answer this question, Geoff is using a very different way of detecting planets. Nicknamed the wobble method, this technique was used to find some of the first exoplanets. And it's also used to find out more about the planets discovered by Kepler.
We can detect planets around other stars even without seeing the planets by watching the star. Let's create a star. And of course, we'd like a planet orbiting that star. Now what's interesting is that the planet not only orbits the star, but the star is yanked on gravitationally by the planet. So we see the star wobble around, and we can detect this with our telescopes here on Earth.
The Keck telescope can see if a star is wobbling backwards and forwards in response to a planet we can't actually see.
But even more beautifully, we can measure the mass of the planet, because the more mass of the planet orbiting the star, the more violently that star is yanked on gravitationally.
If the telescope detects a large wobble, it means a massive planet is orbiting the star.
We're heading to the Kepler field now. So I'm going to set the exposure meter.
Geoff takes aim at Kepler-22.
That gives us Doppler shift precision of about 1.5 meters per second. So we'll be able to measure the speed of the star to within plus or minus human walking speed. Here we go. And there it is, Kepler-22. Looks beautiful.
Even with this high level of precision, Geoff fails to find a measurable wobble, which means that the planet is not extremely massive.
So far, what we can tell is that the planet is probably not purely solid. It's not a big ball of rock.
Kepler-22b could still be a gas world, a kind of mini Neptune. But there's another possibility that's even more intriguing. This planet might be unlike anything in our solar system. A water world.
We do know that as long as the planet is over 7 times the Earth's mass, it could possibly have liquid water at its surface. So Kepler-22b, despite being a relatively big planet, is still in the potentially habitable category.
From the study of other planets, all of those somewhat larger than Earth planets have lots of water and also perhaps some atmosphere. So by association, the bet is that Kepler-22b will be a rocky planet with a very dense and thick ocean.
If Geoff is right, this would be a planet completely covered in water. It's the perfect planet for a paddle. Geoff can imagine what it would be like to kayak on Kepler-22b.
If you were kayaking on Kepler-22b, you'd look overhead, you'd see a host star that would remind you of our own sun here, a yellowish star about the same size as our sun. The gravity of the planet might be a little higher, a little lower than the Earth, but not so different.
But look beneath the surface, and this ocean is unlike anything on Earth.
The ocean would be thousands of kilometers thick. There would be no ocean floor to dive down and visit because it would simply be too far away.
Kepler-22b could have all the ingredients for Earth-like life. Energy is plentiful in sunlight from the nearby star. The necessary elements, like hydrogen, oxygen, carbon, and nitrogen, are commonplace throughout the galaxy. But for life to occur, these elements would have to form into a molecule with a very special property. A molecule that can self-replicate like DNA.
Life is a chemical system capable of Darwinian evolution. We need molecules for life that contain information. We need molecules that can mutate so that that information changes and that can be inherited. I suspect that carbon is going to be the stuff of life, and there will be information-containing molecules such as DNA.
Even here on Earth, we don't know how DNA first came to exist. But even if the creation of a molecule that works like DNA is unlikely, life may have sheer numbers on its side.
It may be that only one planet in a million will give rise to life. But on the basis of Kepler, some people have suggested that there might be 10 to the 19th planets in our galaxy or in nearby galaxies. That's a very big number. And so the probability that life exists elsewhere is pretty high.
It's this emerging statistical fact that leads many scientists to be confident that extraterrestrial life does exist.
Is there life elsewhere? Well, our galaxy alone has 100 billion stars.
If DNA, or a similar self-replicating molecule, has formed on any of those planets, life could have been around for some time.
If we go back to the very oldest sedimentary rocks on our planet and look for the signature of life, it's already there. And that tells us that life arose early.
But early life was limited to simple single-celled organisms. Microbes had the Earth to themselves for billions of years before complex life evolved. It may be that microbes rule our galaxy as well.
The most probable life on other planets would be something much more similar to bacteria than to you or me.
Of course, we don't know how likely it is that complex life would evolve on an alien world.
There's still very much an open question as to whether life could get started in such a water world. But over billions of years, if the climate was stable enough, evolution will have had the chance to get beyond microbial life to forests of complex, advanced trees.
Could plants adapt to life in an endless ocean?
On a water world, the main challenge that these plants are going to face is remaining buoyant. You can't start sinking down if you want to float, perhaps by having bladders filled with gas that help you to buoy up in the water.
While scientists can speculate about life on Kepler-22b, for now there is no way to confirm that there is water on its surface. Fortunately, it isn't the only potential life-supporting planet Kepler has found. On February 28, 2012, nearly 3 years after launch, NASA announced over 1,000 potential new planets. One of these was orbiting the star KOI 2626. This potential planet is about 1.5 times the size of Earth. small enough that it's likely to be rocky. But there's a problem. It doesn't orbit a star like our sun. It orbits a very different kind of star.
When I was a kid, I was told in school that the sun is an average star, which is a complete lie. The sun is not an average star. Most stars in the galaxy are much less massive and put out much less energy than the sun. And we call these very low-mass stars M-dwarfs. Our sun is yellow in color, very massive, very large, and compared to it, these low-mass M-dwarf stars are tiny. They're only about 10 or 20% the size, 10 or 20% the mass, and they only put out 1/1000th the amount of energy.
M-dwarf stars, also known as red dwarfs, make up over 3/4 of all stars in the universe. Because the star is so small, it's easier to spot a small planet orbiting one. Even though an Earth-sized planet covers only about 0.1% of a red dwarf, it typically dims the light by an easy-to-see 1%. Dave Charbonneau and his team have searched through the Kepler data, and they found that more than half of all such stars have planets Earth-sized or a little larger. But could a planet orbiting such a dim star be warm enough to have oceans of water and even life?
An M-type star provides much less sunlight than our star. To get the same amount of warmth, just like this dimmer fire, you have to move in closer. There's still a habitable zone. You can get close enough to the star that it's warm enough for liquid water.
KOI 2626.01 orbits its red dwarf star once every 38 days. But being so near to a star can create a strange situation. Gravity from the star pulls more strongly on the closest side of the planet. A slight drag that can cause one side to always face the star. Astronomers call this tidal locking. This alien world would have a light side on which the sun never sets, and a dark side on which the sun never rises. At first, scientists thought that this would make the planet impossible for life because it wouldn't have an atmosphere.
When we first conceived of the notion of a tidally locked planet, even in the habitable zone, the thought was, well, on the dark side, it's going to be very, very cold. So cold that the atmosphere could condense out completely. All the carbon dioxide that would normally be in the atmosphere would be present as ice, forming a giant polar cap on the dark side. Ice like this. This is a chunk of carbon dioxide.
But atmosphere expert Kevin Hang wasn't so sure. He builds computer simulations of alien atmospheres. He's a kind of interplanetary weather forecaster. Hang used what we know about the red dwarf planet to simulate the atmosphere. And this is what he came up with. A map of the whole planet laid out flat, the colors representing the predicted temperature.
What you're seeing is a temperature map near the surface. Right in the middle of the map is the point where the temperatures are expected to be the highest.
And this temperature difference between the hot side and cold side has a profound effect on the atmosphere. Here on the dark side,